Hello, everyone. How you doing, Mimi?
I'm doing well.
Good. Exciting. Ready for another exciting day of physics? About as ready as you ever be, right? Well, I get to go to the dentist right after this, so that's not quite as fun as what you got planned, probably. Everybody, go ahead and chat your first and last name so I have it on the roll and you won't forget. We're getting there. A lot of people coming in. Almost there. Jamie, were you able to get your lab done, bud?
Is it due today?
No, I'm just seeing if you were able to get it done, if you had any problems or anything. You got a week.
I wasn't having problems, but it's not done yet.
Gotcha. No problem. Just checking to make sure, Make sure you ask me if you need any help, bud. So does anybody have any questions on past material? The test is up now, by the way, and I decided to give you until the 28th at 11:59 p.m. So that's Monday night at 11:59 p.m. So you do get 3 attempts. Each time you take it, it'll be a different one, of course. You get 25 minutes. Ignore the 26 that's said there. All my tests are somewhat comprehensive, so there's some probability that you'll see something from chapters 1 and 2 in addition to 3 and 4. But generally, it's essentially a test on chapters 3 and 4. So today we're going to do chapter 6, which is on gravity. We're not going to spend too terribly much time on it. In fact, we'll probably finish it today.
If we have any problems with the test, like last time, do you want us to email you about it?
Yeah, do let me know. You shouldn't this time. I've checked all the questions again and make sure none of the answers have any weird symbols or anything like that in it, so that all should work. But yeah, always text me as soon as you know. Email me as soon as you know or see something's wrong. Make sure, for instance, if you're having a problem with submitting your test or something weird like that, you might want to take the time to do screenshots of every question with your answer on it before you just go offline. That's one way to protect, because sometimes you'll be in the middle of a test and you'll answer all the questions, and then you'll lose your Wi-Fi connection or your internet access, and that basically leaves it like it's an open test. When that happens, you have no way of showing me what your answers were. So if you finished it, it wouldn't be a bad idea to go ahead and take a snapshot of each of the answers. Even shrink the window down the text down as much as you can to try to fit 3 or 4 questions in one page. Take a shot of them before you hit submit, and that just in case. And then if everything goes through and everything's fine, then you can throw those photos away. But I would literally think about doing that every time, just in case the internet goes out or something weird like that. I can always give you another chance, but that's going to make me make another test for you, because once you've seen the questions, even though they change every time, once you've seen it, say once or twice, or at least once you've seen it twice, I can't just automatically give you 3 chances then. I switched to water. I feel horrible. This healthy stuff is awful. No coffee. All right. Well, I guess we'll go ahead and get started. I've got 21 of you folks in here. So we're working on gravity today, and I've already hinted a little bit about gravity. For instance, I told you the story about how Newton was sitting under an apple tree in his mother's orchard and looked up at the moon and looked up at an apple and realized how they were probably being acted upon by the same forces. In other words, according to Newton's first law of motion, which was really Galileo's law of inertia, the moon should go in a straight line. But since it doesn't go in a straight line, we know there must be some force acting on it. That force, he was arguing, was the same force that causes the apple, once it gets, grown enough that it's too heavy for the stem to hold, will actually break the stem and allow it to fall. So he said, well, if that's the case, then I wonder if this force is dependent on the distance like light is, because he had already been studying light, and he found out that, if you go twice as far away from a light source, you decrease its brightness by a factor of 4. If you go 3 times as far away, you decrease it by a factor of 9, and so on and so forth. So he said, I wonder if it happens to be a force like that. So he said, well, I know the acceleration due to gravity here for the apple is 9.8. And I know we're 1 Earth radius from the center of the Earth. And I know that the moon is 60 Earth radii from the center of the Earth. So if I take 9.8 and divide it by 60 squared, which is 3,600, I should get the acceleration of the moon if that's the true formula. So sure enough, when you divide that, you get 0.00273, I believe. It's 272727 basically. When you actually do that, and then you calculate v squared over r as we did last semester, last chapter, you find out, lo and behold, that's exactly the speed or the acceleration that the moon has to have to be in a circular orbit. So he, at that instant, was the only person on planet Earth that knew basically what caused the planets to orbit the sun. So it was a monumentally awesome discovery. He was able to realize that it wasn't really the final picture, because he didn't understand how something could reach across space and pull on it without physically touching it. But he said, I can solve a lot of problems with this, so we'll leave it as is. And maybe some future people will answer that. That's what Einstein comes back and does in 1911. So Einstein's able to actually come out with general theory of relativity that explains how, in some sense, the sun appears to be reaching out across space and grabbing a hold of each individual planet without touching them, and making sure that they are bent or moved out of their straight paths. So what Newton was able to do, I'll go ahead and share my document camera with you. Whoa, or I'll just turn off my camera because I'm a goober. So what Newton discovered was that this law of gravitational force, which we now call the universal law of gravitation, and that means a couple things. First, universal means it is true everywhere. So that's one way of thinking about the word universal. Another way of thinking about the word universal, though, is that you can't go anywhere in the universe such that you can escape the force. In other words, the force mathematically is never zero. There's no distance away from, for instance, the Earth that you can get where the force on you due to the Earth is exactly zero. So that's a couple different ways to think of it, but it's called the universal law of gravitation for those two reasons. And this is what he postulated. He said that the force is directly proportional to the product of the masses. So we'll say M1, M2, and inversely proportional to the square of the distance between them. Okay? Well, in order to make that into an equation, just like you did in high school algebra, you have to put a constant in there. The constant we use is the gravitational constant of the universe, and that G is equal to 6.67 times 10 to the negative 11th. And the units, notice you have to get out a Newton because that's what the force is going to be. So it's going to have a Newton up top. But it's also got to cancel out 2 meters that are on the bottom, a meter times a meter. So I'm going to say meters squared. And it's also got to cancel out the kilograms right here by it. So I got to put 2 kilograms down here. So that'd be kilograms squared. So that's the gravitational constant of the universe. We've got better experimental data, so you can actually, look in the cover of your book or whatever, and you'll find we know this to a couple more decimal places, and that's all good. But it tells us a couple things. One, it tells us, and I didn't state this yet, but basically the force of attraction, it always is a force of attraction for one thing. So there's never a place where M1 and M2 are repulsive like we have with 2 positive charges or 2 negative charges or 2 north ends of a battery. So unlike electricity and magnetism, this one's always attractive. And 2, the force being a vector quantity has to have a direct that direction is specified by the line connecting this point particle M1 and this point particle M2. So if you imagine M1 and M2 as if they're individual point particles, the line connecting them is the line along which the force acts. When you actually get into cases where they aren't point particles, there's something called the center of mass for each of them, and then you connect the center of masses of each of them, and that line is now the line along which the force acts. Okay, so that's gives you some idea basically what the law of gravitation says. So what we want to do is see how we can work such a law, work with such a law, and see what kind of things we can figure out. So for instance, if you wanted to calculate how much attraction you have between yourself and another student in a classroom situation, because obviously we're not in one now, we could say, for instance, let's say two students are 1 meter apart. So we'll say R is equal to 1 meter. And let's say that each student has a mass of 60 kilograms. So M1 equals M2 equals 60 kilograms. What is the gravitational force of attraction between them? So F is equal to question mark. Well, all we got to do is plug it in. We're going to say 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 60 kilograms times 60 kilograms divided by 1 meter squared. So if we actually do that calculation, we're going to get a god awfully small force, 6.67 e to the negative 11, and I've realized I'm not wearing my glasses and can't see a daggone thing, times 60 divided by 1 squared is equal to 240 times 10 to the negative 9th newtons. Okay, so not a very big force at all. A nanonewton, or actually 240 nanonewtons. So that's a really, really teeny force. One thing you should know about this is, one, since this force is directly proportional to mass, if I were to double one of your masses, let's say it's now me, so it's 120 kilograms, which is pretty close to my mass, really, then this force would double. So I'd have 480 nanonewtons. Similarly, if you doubled this one instead, you'd also double the force, so you get 480 nanonewtons. If you doubled both of them, however, then you get double times double, or 4 times as much, which would be at 960 newtons. Additionally, if you cut this distance in half, notice that's a square there. So you don't decrease the force, or well, first off, when you decrease it, since it's in the bottom and the force is on the top and they're on opposite sides of the equal, they're what I call thumbs up, thumbs down. So when this one goes up, this one goes down, or when this one goes down, this one goes up. So if I go from 1 meter to 1/2 a meter, it's going down, which means this one's going to go up, but it's not going to go up by a factor of 2. It's going to go up by a factor of 2 squared, which is 4. So I could either double the mass of both of the people, or I could put them 50 centimeters apart instead of 1 meter apart, and both would result in a force of 960 nanonewtons. So that's the concept behind all this, is how the force responds. A neat aspect of this, it turns out that the law of electrical attraction is exactly the same form, except we use this constant K instead of G. And instead of mass, we use charge 1 and charge 2, and it's over R squared, just like the law of gravity is. But check this out. This number, like the 6.67 times 10 to the negative 11th, is 8.99 times 10 to the 9th. Notice that's a positive 9, and it's Newton meter squared per Coulomb squared. So you can see already the electric force is way, 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 way bigger. For instance, if you compared the gravitational attraction between the proton and the electron in the hydrogen atom, and then compared that to the electrical attraction between the proton and the electron in the hydrogen atom, you'd find that the electric force is about 1 with 40 some zeros after it, bigger. So it's kind of neat that these forces have this similarity in terms of how they respond. You don't need to know this for this class, so I just wanted to bring that up as a sort of sidebar, if you will. But it is kind of interesting to know that. Now, what that gives us an idea roughly of how small of a gravitational attraction there is between you and another person in your classroom. So you can pretty much ignore gravity when dealing with objects that are, you know, of mundane sizes, like even say between a skyscraper and you. The forces are still quite small, so don't spend much time worrying about gravitational attraction in that sense. Even next to a fat guy like me, it's pretty minuscule. So what we will do though is think about some other things. So maybe we should figure out basically what's the force of gravity acting on, let's say, a spacecraft when it's in orbit around the Earth. So that was one example here. Let's do a spacecraft in orbit around the Earth. So here's Earth. It has a radius of 1 Earth radii. What I'm going to do is go out to 4 Earth radii. So I'll put an E down here so everybody knows that this is Earth radius. And we can actually look up Earth's radius. In fact, it'll be found in the front cover of your textbook. But there's actually easier ways. The radius of the Earth is 6,380 kilometers. So RE is 6,380. Notice I said kilometers though, because that means I got to convert it to meters. And this spacecraft, let's say it's a pretty big spacecraft. Let's say it's 4,000 kilograms. And I'm assuming that's 4 sig figs. This 4 is an infinite number of sig figs, and that's got 4 sig figs, okay? So one thing you can say, if you want to know what the gravitational force on it is, according to Newton's own reasoning, it should be like the force that an apple would feel on the surface of the Earth, only it's now 4 times as far away, so it should be 1/16 of the object's mass. Well, we know the object's weight. The object's weight on Earth is actually equal to, and I'll call this M, and this, by the way, is M Earth, which has a weight, by the way, of 5.98 times 10 to the 4th, or 24th. So the weight for this 4,000 kilogram thing on Earth is mg, which is 4,000 kilograms times 9.8 meters per second per second. Okay, and remember, a kilogram times a meter per second squared is actually a Newton. Of course, we can also realize that 9.8 times 2 is 19.6 times 4 is what, 38.2, 39.2, something like that. So 39.2 times 1,000 would be 39,200. Just guessing there. Did somebody catch me on that?
Would you mind trying to focus a little bit? It's really hard to see those numbers.
Oh, yes. Yeah, and I'll try to write bigger too. Can you see it now? Here, I'll pull it up real quick so we can make sure we got a good scene, at least now. So the radius of the Earth is 6,380 kilometers. The mass of the spaceship is 4,000 kilograms. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And that was the number I got earlier, 240 times 10 to the negative 9th. So when I take 4,000 and multiply it by 9.8, I get 39,200. Whoo, I was right. Newtons. So that's what its weight is on Earth. Now I'm arguing that according to Newton, since this thing is 4 times as far away from the surface of the Earth as say an apple is, then it should be 1/16 the force on it out there. So just as a check, we'll say W on Earth over 16 And we're going to see what we get on that. We'll see. So I'm just going to divide that number by 16, and I'll get 2.45 times 10 to the third Newton. So that's what I suspect the answer is going to be. Well, let's do it with Newton's law of gravity. So according to Newton's law of gravity, we've got 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. I've got the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. I've got the mass of the spacecraft, which is 4,000 kilograms. And I got the distance, which is 4 times 6.380 times 10 to the, not the third, but the sixth, because a kilometer is actually times 3 already. So that's 10 to the 6 meters. And then I got to make sure I square all this down here. So I'll put it in brackets like that. So I'm going to do 6.67 e to the negative 11 times 5.98 e to the negative 24 times 4,000. I'm going to divide all that by parentheses 4 times 6.38 e to the 6. And now I'm going to square that denominator. And I get 2.45 or 2.45 times 10 to the negative. Whoa. I didn't know what happened. 6.67 10 to the negative. Oh, duh. I actually put in 5.98 times 10 to the negative 24th. That's a slight problem. So multiply this by 1 e to the 48. And that should fix it. Yeah, 2.4945 times 10 to the third newtons. So, in fact, I did get the same result. Okay, so notice, yes, that's a big force. The weight of this 4,000 kilogram object is 39,200 newtons. But when it gets 4 Earth radii from Earth, its weight is only 2.45 times 10 to the third. In other words, it's gone from 39,000 newtons down to about 2,000 newtons. And that is the force that actually is going to cause the spacecraft that would otherwise want to go straight, it's going to cause it to deviate and stay in an orbit. So that's how that works. Any questions on that one?
Yes. What's that below the W on Earth? You have it like divided by something?
Yeah, by 16. I'm using the principle that Newton did, where he said light falls off like 1 over the distance squared. So maybe the gravitational force does, and of course, it does fall off like 1 over the distance squared. So I was comparing, taking that distance, which was r, compared to 4r, means this force should be down by a factor of 16, because 4 squared is 16.
Okay.
Okay, so yeah, it's the same argument Newton made when he divided 9.8 by 3,600 to get the acceleration of the moon. Any other questions? So you might actually say, well, that's still a pretty good sized force, and it is. And in fact, if you want to compare it to the force on the moon, that's even more large. So let's do that. Let's look at the force of gravity on the moon. So force on moon. That's going to be G again times the mass of the moon times the mass of the Earth over 60 Earth radii squared. Okay, just because I happen to know that off the top of my head, so I don't have to look up the distance to the moon. For instance, the distance to the moon is about 1.2 light seconds. So if you wanted to try to compute that, that's kind of a neat thing. So I'll put in 6.67 times 10 to the negative 11. I'm going to leave off the units this time. I think everybody gets what the units are. But now I need the mass of the moon, which is actually about 100 times smaller than that of the Earth. It's 7.35 times 10 to the 22. Kilograms. I think I just had someone, yeah, they're coming in. And then, of course, we already know the mass of the Earth. That's 5.98 times 10 to the 24. I said I was keeping off units, but I stuck a kilogram in there because I'm a goober and forgot what I was doing. Okay, so that one's 22 and this one's 24. And now I'm going to say 60 times 6.38 times 10 to the 6. And I got to square all that junk. So when I do that calculation, I get 6.67 e to the negative 11 times 7.35 e to the 22 times 5.98 e to the 24. And I divide that by parentheses 60 times 6.38 e to the 6. And I square that down there and hit enter. And lo and behold, I get 200 times 10 to the 18th. Which is also 2.0 times 10 to the 20th, by the way. And that should be newtons. Any questions on that?
No, but can you just bring it up close like you did the last time?
Yes. Now, one of the nice little calculations you can do is you can compare the force of the Earth on the moon to the force of the sun on the moon. And when you do that, you'll see that the force of the sun on the moon is about half as big as the force of the Earth on the moon. And that's the reason that we have tides and we had waxing during neap tides and all that stuff. That's why they occur, because basically what's going on is, let me draw a picture for you. So you have the Earth here, and let's say you have the moon over here. The moon is actually causing the water, and actually does the continents as well, causes the water to swell up on that side, because according to gravity, this side is actually closer than the center, right? And since it goes like 1 over r, the r going down from here to here is down compared to from here to here, then the force is actually quite a bit larger here, and that lifts the continents and the water up on this side. Now, the center of mass of the Earth-Moon system is actually about 6/7 of the way from the center of the Earth to the center of the to the outside edge of the Earth. So this is the barycenter. This is the point about which the Earth actually orbits with the moon. So its center goes around like this, while the moon goes like that, right? So as you might suspect, that means over here, the force of gravity from the moon is really, really weak because it's farther away than this one was here. And because this thing's spinning about this point, there's a tendency, according to Newton's first law, for the water to stand out on this side, and it turns out it stands out exactly the same amount. So the tide on this side and the tide on this side are 180 degrees apart, and that's why you get a low tide as your part of the Earth rotates through this. It hits a low tide, then about 6 hours later it hits a high tide, then about 6 hours later it hits a low tide, then about 6 hours later it hits a high tide again. But it gets more complicated, because now if you happen to have, let's say, a new moon, then the sun is way over here. New moon means the sun, the earth, the moon, and the sun are all in one line, basically. And what happens is you get just a little bit more of a tide. because the force is about half as big from the sun, and you get just a little bit more on this side too. So during a new moon, you actually have what we call a spring tide. The tide is quite a bit higher, and the same thing happens during a full moon when the sun would be over here, because the same thing happens. The sun this time is pulling it stronger on this side and letting go of it weaker on this side. So the same orientation occurs whether it's a full or new moon. So because the full and new moon, that actually gives you what we call a spring tide, and they don't mean it happened during the month, during the season of spring. They means it's as if the water springs up out of the ocean. Okay. Now, when you have it at first quarter, so if the moon, for instance, was over here, then they're battling. So you've got the tide trying to go high here and here due to the moon, but the sun is stealing some of it and tries to make it hide here and here. So you end up getting a less severe tide, and that's called a neap tide. So the neap tide occurs at first quarter and third quarter. Whereas the spring tide occurs at full and new. Okay, so just a little bit of physics and understanding of gravity, and all of a sudden we can explain tides. Now it's a little more complicated because, come to find out, as the Earth rotates around like this, it's attempting to drag the ocean along with it. So there ends up being a little bit of a lag. So this line from the center of the Earth to the center of the moon actually forces, is not where the actual peak of the high tide is. It's a little angle ahead, and that angle changes based on the local geography of the shoreline and stuff like that. But you could come into any area and find out what that angle is by looking at two tides, say, and then you can predict the tide for all of the rest of that area for any day at night just by knowing where the moon is. But also because of that, now you've got this wad of mass out here in front. That's actually causing the moon to speed up. And since the moon's speeding up, it's slowly drifting away. So we've got all sorts of stuff happening. The moon drifting away, causing the Earth to change its speed. That also causes us to have to change our definition of a day every now and then. We just go and randomly add a second and all stuff like that. So there's a lot of neat little things that happen. But we have now some understanding of how the tides occur. So anybody have any questions on that spring tide, neap tide stuff? Now you might think, what does this have to do, for instance, with 9.8? And I mentioned this to you before, but we know that your weight is due to gravity, right? My weight is m times g. We've derived that before just by using Newton's second law for a free-falling body. But now, since we know about gravity, we know this is due to the gravitational force on mass m from the Earth. So I can say that's actually equal to that gravitational constant times my mass times the mass of the Earth over the radius of the Earth squared. So you can see these m's cancel out right here and here. So lo and behold, guess what? Gravitational acceleration is actually g times the mass of the Earth over the radius of the Earth squared. And that's how you get 9.80 meters per second, okay? So that might make you think, well, obviously g is inversely related to the distance you are from the center of the Earth. So what about Mount Everest? That's the highest place on the surface of the Earth. So what is g on Mount Everest? Or similarly, what would be g at the bottom of the Marianas Trench, which is the lowest place on Earth? So you can actually calculate those things. So what we're going to do is we're going to say g is actually equal to 6.67 times 10 to the negative 11th. Leave off the units again. The mass of the Earth is 5.98 times 10 to the 24th. I'll leave off the unit again. By the way, you can see what happens. This is Newton meter squared per kilogram squared, but I'm only got 1 kilogram. So one of the kilograms is going to go away. So I have a Newton meter, a Newton per kilogram, which is a meter per second squared. And then finally the distance. Well, the height of Mount Everest is 8,850 meters. That's the height of Mount Everest. So I'll separate this with a line so nobody thinks what that is. And of course, the radius of the Earth is 6,380. And that one was actually 6,380 kilometers. So I should say 000 meters. So what you see is this 0 lines up with this 0. This 0 lines up with that 5. This 0 lines up with that 8. And this 0 lines up with that other 8. So all we really should do is probably put a 9 there, and that will even slightly overestimate the effect of being on top of Everest. So I'm going to say 6.39. Make sure my digits are right. This one goes to here. This one goes to here. This one goes to here. Oop. This one goes here. 389. Sorry about that. Times 10 to the 6th meters. And I'm going to square all that. And I forgot I said I'd leave the units off. Okay. So when I do that, lo and behold, I get 9.77 meters per second per second. Now, the Marianas Trench is, I think it's on the order of 11 miles, whereas this is 25,035 feet. So that's more like 5 miles. So actually, you get a bigger bang by considering how much stronger gravitational acceleration is down at the bottom of the Marianas Trench. So this one only changed by 0.03. That one's probably going to change maybe by 0.04 or 0.05, which would make it like 9.84 or 9.85 or something like that. You guys can do that calculation on your own for the Marianas Trench. But any questions on that? So one of the things that you might notice is the Earth actually rotates on its axis, right? And in fact, when you're standing up here on a scale, say, right, and then standing over here on a scale, you're going to get 2 different readings, right? So why don't we figure out exactly what the difference is going to be? What we know is going on here is the scale on top is just going to be, it's going to have a force that's the woman's weight, or the gravitational attraction to the Earth. And that's weight is equal to mg, right? And then acting opposite to that is the force on the scale, okay? And those are the only 2 forces. So we see that weight is actually equal to mg, turns out to be the force the scale weighs, which is good, right? Now over here, we've got a different problem. Over here, what we have is the force of gravity, which is weight, is equal to, sorry, I went too low, is equal to mg. And we have the force on the scale, which I'll call F scale equator, okay, right there. But guess what? This thing, on this spot, I actually have to accelerate. I have to stay in my circular orbit around the Earth, so I have to have an acceleration equal to v squared over r. That's what my acceleration has to be. So the reason this one was 0 is the net force, the summation forces, is equal to mass times acceleration. The acceleration was 0 there, so these 2 were just equal. We had, for instance, Fs minus mg is equal to 0, and that's how I got Fs was just mg. Here, on the other hand, we have Fs sub e minus mg is equal to the acceleration that way. So I have the person's weight times v squared over r, but that acceleration has to go in the direction that we called negative, so I have to put a negative there. So what we see is I can pull the two negatives over here if I wanted, and that would make them positive, or I can just pull them over there, and I'd realize that F, the force on the scale at the equator, is actually going to be equal to m times g plus v squared over r, all of that times a negative, of course, but that just tells you they're in opposite directions. Okay? So how do we figure out what that velocity is? Well, we know that the Earth makes one rotation every 24 hours, essentially, right? So the velocity is actually equal to 2 pi times the radius of the Earth over t for a day. Okay? So I can say negative m times, in this case, 9.80 times 2 pi. The radius of the Earth would be 6.380. And I'm ignoring the bulging of the Earth at the equator, by the way, which is really insignificant. Times 10 to the 6 meters over, now 24 hours is 86,400 seconds. So I'm going to write 86,400 seconds here. And I got to remember all that is squared and then divided by 6.38 times 10 to the 6 meters again. So that's my whole answer. What I'll do is I'll just see what this number is, and that'll tell me basically how much I got to change g by. So I'm going to do 2 times 3.1415, 159 times 6.38 e to the 6 divided by 86,400. Now I'm going to square that. Now I'm going to divide that by 6.38 e to the 6. And I get that this is basically this portion right here is 0. Actually, it's 0.0337 meters per second per second. So basically, being at the equator makes it as if gravity is slightly less by a factor of by a difference of 0.0337. Actually, yeah, that's what happened. It should have been. I forgot when I pulled this over here, this one's going to become positive, but this one's going to become negative. That's what's going on. So everybody catch this real quick. These are negative, and that one's positive. Notice I left this over here. That made it negative, but when I brought mg, that was supposed to be positive, and for some reason, I just pretended that both of them were negative. So I should be getting a difference. So instead of 9.80, we're getting like 9.77. So you can see it's roughly the same as being at Mount Everest if you're at the equator. Ain't that neat? Any questions on that one?
Yes. Are you able to zoom in at all?
Yes.
Thank you.
And like I said, I always post these notes on my Google Docs that you can access it on our Canvas page. Can you see everything now? Now that sort of is the rundown on all the different stuff. You can do calculations to find out like what's the radius of an orbit for that's geosynchronous. For instance, like the satellites we use for DirecTV and Dish Network, they're geosynchronous orbits. And what that means is as this Earth is rotating, say this way, they put a satellite up that rotates at exactly the same rate, so it's always over the same spot on Earth. So when you see commercials, the commercials actually have to vary from location to location on the surface of the Earth. Like when we see a commercial for a satellite Wi-Fi or satellite internet company, they'll say, as long as you've got a clear view of the Southwest or something like that, that means their satellite is directly above the Earth, southwest of us. But if say it's above northern Texas, if you go to say California, then they're going to need a clear view of the southeast. So that's a kind of neat thing, but that's a geosynchronous orbit. And basically all you're doing then is you're setting the force of gravity, which would be G times the mass of the planet times the mass of the satellite, over the radius of the satellite's orbit, which is obviously bigger than Earth, right? And that's going to be equal to m, the mass of the satellite, times v squared over r. And v is just 2 pi r divided by the period. So you want the period to be a day again, just like I did here. And with that calculation, you can figure out what r is. So that's one way, or one of the types of problems you can actually solve. I'll just write what I said there here. So we had g times the mass of the satellite times the mass of the Earth over the radius of the satellite orbit squared. Okay, that's going to be equal to the mass of the satellite, which, notice conveniently those two cancel out, which means whatever thing we want to put out there, the mass doesn't matter. We're still going to do the exact same thing. And now I'm going to say that's equal to v squared over r. So that's 2 pi times the radius of the satellite's orbit over t, day again, squared over the radius of the satellite's orbit again. So because this m satellite disappears, when you've done this calculation for a satellite, you did it for a human astronaut that we just want to leave because he was a jerk. Or it's still the same for, you know, a car, a Tesla that you want to put out there in orbit around the Earth, right? So that's how you go about doing a geosynchronous orbit. You can solve for r, and you find specifically that it has a very specific radius. It's in fact, I think your book did it was 7. I think the radius was 4.23 times 10 to the 7th meters. So 4.23 times 10 to the 7th meters. So remember the radius of the Earth was 6.38 times 10 to the 6th. So this is almost a whole factor of 10 farther. So we're looking at around a factor of 9, say. So 9 Earth radii out is a geosynchronous orbit. You can also do things like the calculation I did here with the scale. You can do the same type of calculation with a human sitting in an elevator. So if you have a scale right here and a human right there, if the elevator is accelerating upward, then again, you have the force of the scale, Fs, and you've got the mg. Those two forces have to add up not to give you 0, they have to add up to give you m times a. So you end up getting, and this is why you feel it too, when the elevator first takes off, you feel like you're a little heavy. And then when the acceleration goes in the opposite direction, i.e. when the elevator starts to slow down, you end up feeling a little lighter. And that's, again, because now these two forces have to add up to give you a force in this direction, because the acceleration was that direction when you're slowing down. So those are the types of problems you can solve with that. The bigger ones that are a little more complicated are really when you're calculating, say, a distribution of masses. Let's say you have an object here and an object here and an object here, right? And I give you these distances, say, and these angles. Like I give you this angle and this angle, say, I don't even need that angle. Well, yeah, I do. And I give you these distances, D1, D2, D3, and these masses, M1, M2, and M3. That's a very typical problem you have to solve, but this is just a vector problem. Remember, if I want to know the force on M3, then I know it's going to act along this line. That's why that angle helps me, so I can get the X and Y components. What I do is make this into my X axis, for instance, and that would make life really easy. But I know the vector force is going to be along this line. So I do G M2 times M3 over D3 squared. That gives me the magnitude. I take the cosine of this angle. That gives me, since it's, remember, this is an actually attractive force. So that means the force is actually acting this way, which is a negative X component. So I do negative cosine of this angle, and that'll give me my X component. And then I do a negative sine of that angle. That'll give me my Y component. And then I do the same thing for this one here, this force on that one, and add those two together as vectors. And now I got the force on M3. So that's a very typical problem. I'll probably work one of these for you Monday. We've run out of time now. But I'll work something like this Monday, and or I'll post one on my YouTube channel. So I'm going to send you, actually, I think you all probably subscribe to my YouTube channel. And when you do that, you can turn on the announcements, and every time I post something, it'll let you know. So I would recommend you doing that at least until the semester's over. I mean, you can dump me later, that's fine. But that'll be a lot easier than having to find out just by trial and error when I do it. Also, it's kind of complicated for me to email all my students at once. So please take advantage of that by, subscribing to the YouTube channel till just so you can find out what I post. Also, it'll be valuable for you next semester because I've actually got a lot of work done on there from the second part of this course as well. So does anybody have any questions?
I don't have any questions about what we've covered today, but I did have a homework question from the last chapter,
Okay, let's go for it.
or chapter 4, I mean.
And
it was
everybody's free to go. Hold on a second, if you don't mind. Everybody's free to go. Just make sure you've chatted me your first and last name before you do so, but I'm going to wait here till the last person gets their questions answered. So, yeah, go ahead and, was it Emma? Is that who I was talking to? Yeah, go ahead. Tell me what question you got. And you can share screen if you need to.
Okay. It was, yeah, I'll do that. So it was a maximum and minimum force problem.
Okay.
And I didn't know how to figure that out, but let me pull it up real quick. Let's see. Okay. Okay, there we go. All right, can you see the screen?
I can.
Okay, just making sure.
So it says the elevator mass 4,750 kilograms is to be designed so that the maximum acceleration is 6.40 times 10 to the negative 2. Notice that's a G, so they mean multiply that by 9.8 meters per second per second.
Yeah.
Okay, and what is the maximum force the motor should exert on the supporting cable? Okay, so in that case, what you're trying to do is you've got to not only lift this weight. Let me, can you still see my pad over here in the corner? Okay, so I'm gonna try to draw it big so it'll make some sense to you.
Okay.
But what you have is an elevator that's like this dot, okay?
Yeah.
You have acting on that elevator is the weight, which is the mass of the elevator times G.
Okay.
Did I draw that big enough?
Yeah.
You also have acting on it this tension in the cable, right?
Okay.
Well, this tension minus mass of the elevator times G has got to be equal to the mass of the elevator times the maximum acceleration.
Okay.
So the tension ends up becoming mg plus ma. So you're gonna, you're going to multiply this by 9.8, this 4,750. You're going to multiply that by 9.8. And then you're going to multiply 6.40 times 10 to the negative 2. That's going to be multiplied by 9.8, but it's also going to be multiplied by 4,750. And then you're going to add those two numbers, and that'll give you your F max.
Okay, and what about the minimum?
Let's say the maximum acceleration is this. The minimum force will be basically when you just have enough to hold the elevator up, not accelerating. So that's just its weight, 4,750 kilograms times 9.8.
Okay,
Does that make sense?
yep, thank you.
Let me see. Actually, hold on. You could actually, I can see a scenario where it would actually be accelerating downward with that same acceleration.
Yeah,
In which case you have T, I'm going to try to write again big enough. You have T minus mass of the elevator times G equals negative mass of the elevator times A. So actually, no, the minimum shouldn't be that. The minimum should be this right here, which is T is equal to mass of the elevator times G minus the mass of the elevator times A. So
Okay.
don't just do the weight. There is an actual minimum, and that would be it.
all right. Okay, thank you.
I think if that doesn't do it, I think that's what they're meaning. But if that doesn't do it, try the other result. Looks like you got 5 attempts, so you should be good to go.
Yeah, all right, awesome.
Anybody else have any questions on that or anything else? All right. Well, like I said, you're free to go, or you're free to ask me any questions. I'm just waiting for the last person to leave, and then I'll leave.
Okay, I hope you have a great weekend and see you on Monday.
You too, Jennifer. Thank you. Elliot, anybody else have any questions? Emma did. Okay, that's cool. All right. Well, I guess Elliot left, so I'm out of here.